Hey guys, so today's lesson we are going to be doing conditional probability and tree diagrams, and we are using the context, can you get a pair of aces or a pair of kings? So there's a game, and the rules of the game are pretty simple. You have 5 cards total, 2 aces and 3 kings, and I kind of made a slight visual. I just copied the aces and the kings over here. So we've got 2 aces and 3 kings. I just have a deck of 5 cards. The player chooses their first card and records the result, and then chooses their second card without replacement. So that means once I pick a card, I don't put it back in the deck, and then I record the result of the second pick. The player wins if they get a pair of aces or a pair of kings. So we are going to play this game 10 times each. So if you have a deck of cards and you have 3 kings and 2 aces you can pull out, that's great. If you have some scraps of paper or index cards or post-it notes, something that you can make your own fake 2 aces and 3 kings, and play the game recording your results. So I'm going to play the game. I'm going to start dealing my cards and see what I get. Let's see, the first time I get. Alright, and I'm just going to go through. You can do the same right now. If you need to pause the video, you can to fill yours in. Second time, got a king, and then an ace. So again, no win. Next time, 2 kings, so I won. So again, you can be doing this on your own. You can collect your own data if you don't believe me and my data. Winner again. All right, so I've played and these are my results. So maybe you have your own results now as well. Based on the 10 games, what is the probability of winning? So just based on my own personal 10, I have 1, 2, 3 cases out of the 10 where I've won. So to find that probability, that's 3 out of 10 or 0.3 probability that you win the game. Now, we are not together in class, so we cannot record our data at the front of the room, unfortunately. But I'm just going to give you some data that has been collected by other people. So we're going to use the data that has been collected before us, and the probability of winning this game, 116 games were won out of 300 games played. And so this gets us a probability of 0.387. All right, now we're going to use a tree diagram in order to calculate the theoretical probability for all of these different possible outcomes. So I'm going to fill in each blank with the correct probabilities. And if you are following along, if you want to pause and try to fill this in, see how you do first, and then come back and you can watch what we do. So in the ace game, the first step is to deal a card, right? Pick one card, and the probability that that first card is an ace, well, there's 2 aces out of the 5 cards total, so that's 2 out of 5. And now the probability that the first card is a king, well, there's 3 kings, so that's 3 out of 5. So we have our ace, and then we have our king. Now, after I pick out, let's start with the ace, the top part of the tree diagram. After I pick out the ace, now my deck looks a little bit different. I only have 1 ace and 3 kings. All right, so after that one is gone, what is the probability that I pull an ace card? Well, that's 1/4. And then the probability that the second card is a king, well, there's 3 kings out of 4 cards total. So notice how the probability has changed now from before, and that has to do with the fact that there is no replacement in this, right? Now I only have 4 cards to choose from, and the probability of pulling each different card is different. All right, then for the king example, now I've gotten rid of 1 king, so we have 2 aces and only 2 kings. So now the probability here of pulling the second card is an ace, that is 2 out of 4. And the second card is a king is also a probability of 2 out of 4. Now, to find the final probability, so like this first branch here, first card is an ace, second card is an ace. This probability is the probability that the first is an ace and the second is an ace. So this and probability we find through multiplication. So in order to find that, I'm going to multiply the probability of the first ace, so 2/5, times the probability of the second ace, 1/4, and I get 2/20 as the probability for first ace and second ace. So I'm going to keep filling these in. The next one, first ace and second card is a king, is going to be 2/5 times 3/4, which is 6/20. Then we've got 3/5 times 2/4, 6/20. And then 3/5 times 2/4, 6/20. Now 4 says, find the theoretical probability of winning the game. So in order to find the probability of winning, I want to add together the probabilities of the branches where I won. So for the ace game, if I draw an ace the first card and an ace the second card, that is considered a win. So this one up here would be considered a win. And then the other win is if I pull a king and then another king. So that would be this one right here, considered a win. So that's 2/20 plus 6/20. So that's 8/20 total, which equals 0.4. That is our probability of winning the game. Now, before we move on, I just wanted to add some of my own notes to our tree diagram here. So the first thing I want you to notice is these probabilities over here, the 2/5, the 3/5, that is the probability of the first card. So for example, this right here is probability that the first is an ace card. Then we move on and we find the probability, for example, that the second is an ace card. But notice that it's not the same as just the probability of an ace, right? It's a different number than the first one. That's because right now, this is the probability that the second card is an ace. But given that the first one is an ace, right? Because technically down here, this is a second card ace as well, but these two probabilities are different. That's because this one up top here, this and this are different. That's because this one is given that the first one was an ace. Down here, this is the probability of a second ace given the first is a king. So when you're filling out the tree diagram, you have the givens or the conditional probabilities in the second branch. So now in our final box here, this is that and probability. So the probability of A and B, which now we have a little bit of a formula for. It is the probability of A times the probability of B given that A has already happened. and that is the general multiplication rule. So we learned earlier in this unit about the general addition rule. Now we have the general multiplication rule that we use for the AND probability. Now, another thing I want you to notice, at the end of this tree diagram, we have our 4 possible outcomes. And these 4 possible outcomes are all of the potential outcomes you could have. So if you notice, if you were to add all of them up, 2 over 20, 6 over 20, 6 over 20, 6 over 20, because those are all possible outcomes, I expect that the total in the end should equal 1. And if you did that, 2 over 26 over 26 over 26 over 20, you would see that they do in fact equal 1. So that's something we expect, and it's a great way to check your work when you're making a tree diagram. All right, question 5 here says, what is the probability that the first card was a king given that the person won the game? So this is a little bit backwards than how we've been thinking about it. I am looking for the probability that the first card was a king given I know the person won. Now, in order to find this probability, it'll be helpful to use our probability conditional probability formula, right? So that's where we find the probability of A and B and divide by the probability of B. So this is equal to the probability of first king and 1. So I'm going to look back up at my table. The first king is down here, and to win, I would need the second to be a king. So that probability is 6 over 20 from right here. So that's going to be 6 over 20 over the probability just that you won. Well, we found that right above. The theoretical probability of winning is 8 over 20 from question 4. So I want you to notice the denominator is always from your condition, the probability of whatever the condition is. The numerator is the probability of both the given or the condition and the other probability. So it's both events together. And now this equals 0.3 over 0.4, which equals 0.75. So that is the probability that the first card was a king, given that I know the person won the game. All right, let's move on to the important ideas then. So for our first important idea, we're going to create 2 sections. We actually have 3, but one of them's kind of small. So we're only going to divide this into half. It is about the general multiplication rule. All right, so the general multiplication rule is the probability of A and B is equal to the probability of A times the probability of B given A. And so remember that this vertical line here is that given that A happened. And we know that this is considered a conditional probability. All right, now we can actually simplify this if we know that 2 events are independent. Very similar to how we have the general addition rule and then we have a simplified version. So if A and B are independent, think for a second, how might this simplify my equation? What might happen if A and B are independent? Well, from what we learned yesterday, if they are independent, that means that the probability of B given A should be equal to just the probability of B. So our simplified equation then is going to just be the probability of A and B equals the probability of A times the probability of B. So you're probably more used to the simplified version, but sometimes we have conditional probabilities because events are not independent. So again, this first one right here will always work. You don't have to use the simplified equation, but if you feel familiar with these, you feel comfortable, you can then move on to the simplified if you know the events are independent. All right, our next learning target is about tree diagrams. So I'm going to give an example of a tree diagram just using kind of like variables for my events. So starting here, I'm going to say that we have event A, and we'll make the other one just event A complement. So we have A, and then we have A's complement. Then from A, I'm going to move this down a little bit. We are going to get, let's say that we have option B or C. So we have either B could happen or C could happen. And then, of course, that could also happen if A complement happens first as well. And so what we have then at the end is every potential outcome. So like this right here is the probability of A and B. Then the second outcome, this is the probability of A and C. This third outcome is the probability of A complement and B. And the last one is the probability of A complement and C. And I also want to add in here some of those probabilities as well. So remember, we always start with the probability of just the first event, so probability of A, or the probability of A complement. And then it becomes conditional probabilities, right? After A happens, then my probability here is the probability of B, but given that A has already happened. This next one is the probability of C, given that A has already happened. And the next two, now we're assuming that A complement has happened. So the probability of B given A complement has happened. Sorry, guys. Probability of C given that A complement has happened again. All right, so we have those there. And then also remember that at the end of your tree diagram, you have come up with every potential outcome. So if you were to total all of these probabilities up, they should add to 1. Now our last learning target is kind of like a, I don't know if I'd call it a helpful hint, but when you are trying to find probabilities, sometimes you might be asked to find the probability that at least 1 happens. So find the probability that at least one person decides to go to college, right? That can be kind of hard because the probability that at least one person, say in our first period class, could be one person, could be two, could be three, could be anywhere between 1 and 30 people deciding to go to college. So it can be really hard when a question asks you to find the probability of at least one. But we can kind of use the idea of complement, right? The probability that at least one is like the complement of if nobody goes, right? So the probability of at least one is equal to 1 minus the probability of none, because it is the complement of no one going, right? Either no one goes or at least somebody goes. So in order to find a probability that says at least one, you can use the kind of like formula, 1 minus the probability that none happens. All right, so there's the lesson. Let's continue on to the check your understanding. See how you do, if you can do them on your own, so pause the video, and then I'll go through each of them and give in some extra additional notes as well. All right, so at this point, hopefully you've paused. I'm going to go ahead and start by constructing my tree diagram for part A. So we have all of our states here. And the first branches of our tree are going to be the two parties. So Republican and Democrat. And for Republican, that was 30 out of 50. And for Democrat, that is 20 out of 50 for our probabilities. Then, within each, there's two options. You have either continental U.S. or not continental. So we're going to have continental or not. And the same thing repeated for the Democrats. Now for the Republicans, we saw that 29 out of the 30 were continental U.S. So that would be the probability here. And only 1 out of 30 for non-continental. And for the Democrats, it was 19 out of 20 and then 1 out of 20. So now in the end, then, we can find our final probabilities for each of these outcomes. So for the first one, the probability of Republican and continental U.S. is 30 over 50 times 29 over 30. So that equals 29 over 50. For this next one, we get 30 over 50 times 1 over 30, which equals 1 over 50. For the next one, 20 over 50 times 19 over 20 equals 19 over 50. And the last one, 20 over 50 times 1 over 20 equals 1 over 50. All right. So now, one thing that I would like to add to what we have here is just that, if you notice, in the end, when we have all potential outcomes, they do in fact add to 1, just like we thought they should. All right, so there's our tree diagram. Moving on, for B, I want to find the probability that a randomly selected state is in the continental US and went Republican. So I'm looking for the probability of continental and Republican. And what's really nice about our lovely tree diagram is we already have this probability found for us. Continental and Republican is the Republican and Continental branch right here, 29 out of 50. So that's how you would use your tree diagram. And then to write this as a decimal, 0.58. All right, part C, and this is the one I kind of warned you about before. If we select 4 states at random with replacement, so that means we are putting them back in, what is the probability that at least one of the states is in the continental US and went Republican? So what I would do is the probability of at least one equals 1 minus the probability that none. Okay, well, how am I going to find the probability that none? In part B, we just found the probability of continental and Republican. So how would I find the complement of that? Well, the complement of continental and Republican, I'm going to say C and R complement, is equal to 1 minus 0.58 equals 0.42. This is the complement of continental and Republican. So this would be that they did neither, right? If I want to know that at least one state did... All right, sorry guys, I just had to pause, so I don't quite remember what I was saying, but let me just go over that again. So in part C, I'm finding the probability of at least one, so that at least one state is in the continental US and went Republican. And in part B, we just found the probability of a state being in the continental US and it goes Republican. So in order to find this at least one, so I want at least one state to fall into this category, I'm going to find the probability of 1 minus, or I want to find it by doing 1 minus the probability of none. Now, this probability of none right here, ooh, that's a bad color for this. The probability that none of the states went continental and Republican, I need to know the probability that they are not continental and Republican. So that's going to come in by finding the complement of continental and Republican, which is 0.42. Now, if I want all 4 states to not be continental and Republican, then I'm going to take that same probability and I'm going to raise it to the 4th power. Because remember, in order to find the probability of this and this, I just multiply them together. So if I want to know the probability that state 1 is not continental and Republican, and state 2 is not continental and Republican, and state 3 is not continental and Republican, and state 4 is not continental and Republican, then I would multiply their probabilities together, which is just doing the same number times itself 4 times. So what this becomes is 1 minus 0.42 to the 4th, which equals 0.9689. I'm going to move on to part D in case people are understanding that. But if you're not, let me come back to it after I finish part D. So some people can leave if they need to, and then I'll just go back over it once we've kind of cleared our heads and are ready to think about it again. All right, part D. Given that a randomly selected state is not in the continental US, what is the probability that they went Republican? So I'm looking for the probability of Republican given they're not in the continental U.S. So in order to find this probability, I would set it up, and I'm going to get 1 over 50 out of 1 over 50 plus 1 over 50, which in turn will equal 0.5. Now, where did I get those numbers from? Remember, the numerator is the probability of both, so the Republican and not continental. Technically the union, right? Not the. And then the denominator is just the probability of the given. Sorry, not the union, the intersection. So let's just rewrite the formula so we remember what it is. Probability of A given B is equal to probability of A and B over probability of B. So a Republican and continental U.S. is 1 out of 50 over 1 over 50 plus 1 over 50. So we get 0.5 there. All right, so that concludes the lesson. I will go back up and kind of re-explain C, just because I felt a little bit like maybe I was talking too much. So I thought a clean slate might be good. If you're good with that, though, you are free to go. Hope you have a good day, and I will see you later. So just to reiterate one more time. If I want to find the probability that at least one of the 4 states is in the continental U.S. and went Republican, it's easier to find the probability that none of them did, and then use the complement to find at least one. So the reason is because if I want to know at least one, that means 1 state could be it, 2 states, 3 states, 4. So instead, I just find the probability that none of the states are continental and Republican. So to find the probability that none of them are continental or Republican, that's what we got from up here. So that was the not continental and Republican, so the complement of that. And we found 0.42. And then really that probability of none, that is the 0.42, right? That is the probability that a state is not continental and Republican. But to find that none of the states out of the 4 are continental and Republican, I raise it to the 4th power because there are 4 states. So right here in orange is the probability that 0 of the 4 states are continental and Republican. Then I do the 1 minus that probability in order to find the probability that at least one of them is. Okay, I hope that helped a little bit more if you were still confused with that. If you are still confused, send me a remind or ask me at some point, and be happy to go over an explanation with you where we can actually talk with each other. All right, bye guys.